Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
All right, this is Week 9, Part 1. And today we're diving into one of the most creative ideas in all of modern AI, Generative Adversarial Networks, or GANs for short. Now, this isn't just another model. It's a totally different way of thinking. We're moving away from the old method of just trying to minimize some error, and we're stepping right into the world of game theory, a world where the goal isn't just to win, but to find a perfect balance, an equilibrium between two competing forces. And to really get our heads around this, we're going to use an analogy that's going to stick with us through all the math. Just picture this. You've got a master art forger, right? Their one and only goal is to create fakes that are so perfect they're completely indistinguishable from the real deal. But hot on their trail is a brilliant detective, a true expert whose entire career is built on spotting even the tiniest flaw in a forgery. This constant duel, this cat and mouse game, is the absolute heart and soul of how a GAN works.
So this brings up a really key difference in how GANs actually learn. You see, older models like VAEs, they try to write down a rule book, an explicit formula for what makes, say, a masterpiece painting. Our forger, the GAN, doesn't do that. It works with something called implicit density. It doesn't need a rule book. Instead, it has a process. It's kind of like a black box that just learns to create these masterpieces by getting constant feedback on what fools the detective and what doesn't. It's learning by doing, not by studying a bunch of theory.
Okay, let's formally introduce the two stars of our show. First up, we have the generator. This is our forger. Its job is to take a bunch of random noise, think of it like a blank canvas or just raw inspiration, and transform it into a piece of fake data, like a photorealistic image. Then we have the discriminator, our detective. It gets shown a mix of real images from a dataset and the fake ones from the generator, and its only job is to look at each one and say, what's the probability that this is real? Now, every game has to have rules, right? And in the world of GANs, those rules are written in the language of mathematics. We're about to look at what's called the objective function, which is basically the scorecard for this whole competition. It's what tells us who's winning the duel between our forger and our detective. And here it is, the scorecard itself. This is the famous minimax equation. I know, it looks a little scary, but let's just break it down. On one side, you've got the discriminator, that's D, who is trying to maximize this entire value. It scores points by correctly identifying real data, that is, making D of X close to 1, and by correctly spotting fakes, making D of G of Z close to 0. But on the other side, you've got the generator, G, and it's trying to do the exact opposite. It wants to minimize this value by creating fakes that are so good, the discriminator thinks they're real. It's a perfect tug of war. So let's just put that in plain English to make sure it sticks. The detective's whole goal is to maximize the score, to be the best critic it can possibly be. And the forger's goal? To make the detective's job impossible, to minimize that score by crafting forgeries so perfect they just sail right through as authentic. Their goals are in direct opposition. Okay, so that's the game, but what happens when both players are absolute masters? What's the end game when our forger is Leonardo da Vinci and our detective is Sherlock Holmes? That's what we're going to dig into now, the beautiful theory behind the perfect equilibrium of a GAN. And we're going to walk through this step by step, nice and logical. First, we're going to figure out what a perfect, unbeatable detective would actually look like. Then, we'll solve for their optimal strategy. And once we have that, we'll see what that forces our forger to do if it wants to stand any chance at all. So for step 1, we need to find the optimal discriminator. And to do that, we treat this like a classic optimization problem. We take that big value function from before, and we use a bit of calculus to find the exact point where the detective's performance is at its absolute peak. We're essentially writing down the mathematical definition of a perfect fake spotting strategy. And once you solve that equation, you get this really elegant solution. This tells you the perfect detective strategy. Their optimal decision is just the probability of the data being real divided by the total probability of it being either real or fake. In other words, if some image is way more likely to have come from the real data set than from the forger's workshop, the detective will be very confident it's real. And you can see that on the graph. The output shoots up to 1 where the real data is and drops to 0 where the fake data lives. Okay, so now we know the detective's perfect playbook. So assuming our forger is up against this unbeatable opponent, what does that mean for them? Well, to figure that out, we take the formula for our perfect detective and we plug it right back into our original scorecard. We're now looking at the game purely from the forger's perspective, against a detective that cannot be easily fooled.
And after you do some rearranging, something incredible happens. That whole complicated minimax game, it just simplifies down to this. The generator's real goal becomes minimizing something called the Jensen-Shannon divergence. Now, divergence is just a fancy math term for a measure of difference. So the big takeaway is this. The forger's ultimate goal is simply to make their art as similar as humanly or, well, computationally possible to the real art.
And that leads us to the grand finale of our theoretical game. The win condition for the generator happens when that difference, that divergence, is zero. And that only happens when its data, PG, becomes identical to the real data, P data. At that exact point of equilibrium, the forgeries are indistinguishable from the real thing. The detective is completely stumped and is forced to just guess, outputting 0.5 every time. The forger wins by forcing a perfect tie.
So, that was the beautiful, clean world of theory. It's elegant, right? But when we actually try to train these networks, things can get pretty messy. The game doesn't always play out like it's supposed to. So let's take a look at what happens when this perfect game breaks down in the real world. This right here shows one of the biggest problems you'll run into, the vanishing gradient. This happens if our detective gets way too good way too early. Look at that blue line. When the discriminator is super confident that something is fake, meaning its output is close to zero, the slope of the graph gets almost perfectly flat. A flat slope means a zero gradient, and a zero gradient means the forger gets zero useful feedback on how to get better. It's like the detective just shouts, "fake," without offering any clues as to why. So, how do we fix this? Well, with a clever little trick. Instead of telling the forger, your job is to minimize the chance of getting caught, which is what leads to that flat line, we flip the script. We tell it, your job is to maximize the chance of fooling the detective. They sound similar, but mathematically, they're very different. As you can see by remembering the red line on the last graph, this new goal gives a really strong learning signal, a nice steep gradient right at the beginning when the forger needs it most. But the vanishing gradient isn't the only pothole on the road to building a perfect GAN. Let's quickly go over a couple of other common glitches you'll see when you play this adversarial game. A classic problem is something called mode collapse. This is basically when our forger gets lazy. It discovers one specific type of fake, maybe one particular face or one breed of dog, that reliably fools the detective, and then it just produces that same thing over and over and over. As the picture shows, the real data might have all this wonderful variety, but the generator just collapses down onto one single mode, completely ignoring the rich diversity it's supposed to be learning. And another really tricky issue is the disconjoint support problem. This tends to happen early on when the generated fakes are just so obviously different from the real data that their distributions don't even overlap. A perfect detective can easily draw a line right between them and say, everything over here is fake, everything over there is real. But again, that perfect separation leads to a zero gradient. The forger gets no useful information about which direction to move in to make its fakes any better. So, let's just tie this all together. The adversarial equilibrium in a GAN is defined by a super clear objective, that minimax game. And the optimal solution is beautiful. The generator learns to perfectly copy the real data. But in the real world, actually getting there means you have to navigate some serious challenges, like vanishing gradients, mode collapse, and these disjoint supports, which all conspire to stop the forger from getting the critical feedback it needs to learn and improve. You know, this constant dance, this competition between a creator and a critic has unlocked some absolutely staggering levels of creativity in AI. We're seeing images, music, and text that are just jaw-droppingly realistic. And it leaves us with a really fascinating question to chew on. What other incredible breakthroughs are waiting for us when we apply this powerful adversarial idea, this competitive learning, to problems that go far beyond just making pictures? What happens when we teach AIs to compete with each other, to solve some of the biggest challenges we face?